Good afternoon, everyone. It's a delight to be here. I'm a data scientist, and I'm currently working for a gaming company where I get to play with different machine learning platforms because we are upgrading our machine learning pipeline. So among that includes different data science platforms, machine learning frameworks, and I get to build different projects like churn prediction, recommendation system, fraud detection systems. Prior to that, I worked with Databricks, SkyMind, company behind Deep Learning 4J, and Wikipedia during my master's in data science. So these are some of the demos that I'm going to show today. The first demo will be focused on community edition of Databricks with MLlib Word2Vec, and the second demo would be on sparkling water of like H2O and Spark's combination. So this is the quick agenda. So this is a graph that shows number of editors on Wikipedia. As you can see, there's a sharp decline from 2007. I have been Wikipedia ambassador from 2010, and I contribute to Wikipedia. I'm pretty sure that most of you use Wikipedia pretty often, and it has been a problem in terms of getting more and more articles. So that's the first challenge. So the goal was to create recommendation engine for Wikipedia editors to make their tasks easier. So the first problem is we have 295 different Wikipedias. As we know, we use English one predominantly, but we have German, Arabic, Indian languages. So there are many different platforms. The problem with traditional recommendations engines are they focus on text, which is NLP approach. Even Stanford's NLP has limitations of 5 to 6 languages, so Chinese, Arabic, German, and obviously English. So we wanted a solution that scales across all the languages. The obvious solution was to go for the text, but as I mentioned, it doesn't scale across all the languages. People recommended us to use the links as well. So I'll just show you the data set that we use on Spark platform. So this graph shows you clickstream database. And for example, when I say clickstream, the San Francisco Wikipedia article gets most of its traffic from Google search engine, and then another Wikipedia sources, and California's Wikipedia page. And most of the people from San Francisco go to another article, such as list of people from San Francisco, and so on. So this could be one approach for recommendation engine. But the problem with this approach is it doesn't consider the reading habits of users. When you're reading Wikipedia articles, you tend to read articles that are in the news. For example, you would read Bernie Sanders' article along with Hillary Clinton and so on, election-related articles. So they don't necessarily have links between them. The data sparsity issue is among the worst ones because, as I mentioned, Indian languages don't really have a lot of articles written in them. So there's definitely not enough data to create separate models. Just want to show you what kind of data we are dealing with. So this is live edit stream of Wikipedia. This is clearly a big data challenge. And for that purpose, we switched to platforms such as Scala and Spark for obvious performance issue. At this point, I don't really have to explain why Spark and Scala is ideal choice for this purpose. So we used Word2Vec. How many of you have heard about Word2Vec? So Word2Vec is the algorithm that basically predicts locally. So in this scenario, this is taken from Stitch Fix Awesome blog, where they are predicting all the words that are around awesome based on the context of awesome. So if you have amazing word, they would predict it based on this. So it's basically words in form of vectors. So in this case, when we have limitation of not using textual data, I use reading sessions. So for example, instead of using text, I'm using number of articles that you're reading one after the other to train my Word2Vec model. Because sequential data works really well with Word2Vec. So these are the preliminary steps, and I have some Scala scripts on my GitHub which you could use to scrape the data and load it in your Databricks notebooks, and you can start using this model and do fun stuff with it. So this is the clickstream scraping, which used to take 1 or 2 hours, but with Spark and Scala integration, it only takes 19 seconds to scrape 1 or 2 GB data. So we broke, these are the few steps I took while breaking down the request per client. So we made sure that we are only using editors' data, and we made sure that they are highly contributing editors to understand the better patterns. And turns out we have 370 million training sessions and 1.4 billion training items across all. only English Wikipedia embedding have more than 170 million embeddings and 650 million training sessions. So what is embedding? Embedding is basically representation of all those reading section in form of vectors. And we push this to a matrix, and then the traditional recommendation engine approach comes into the picture. We just find the articles or vectors that are closer to each other in the vectors. So this is the output. I'm using Spark's TSNA library. So this shows an interesting, this is the data from last month, and this shows that Donald Trump's article is being read together with Melania Trump, Ivanka Trump. These are totally making sense, but people are reading House of Cards articles along with it. So it's kind of ironical, but it seems like it shows the pattern of articles that are being read together pretty clearly now. So the best advantage of this approach is we are not focusing on not just links and text. We are also considering the different arrays of signals that are coming from different people globally. So we are focusing on search engine patterns. We are searching on current news and all sort of other actions that human influence Wikipedia in a way. This is clearly multilingual, and we tested this framework on Chinese languages and Japanese. It shows a pattern of clear succession. So the future work is we would use this for translation. So for example, the articles of Barack Obama are really, really well written in English, but they're not well written in other languages. So if we use this recommendation engine for that approach, it would automatically translate it and create Indic languages and German languages databases and articles more richer. We can also use link recommendations for this. So for example, if we have seen a pattern of using political articles being read together one after the other, we can just put links onto the Wikipedia articles and then make it easier for readers to move along the Wikipedia. So the next demo would be about sparkling water. It focuses on stock exchange prediction, and this is one of the products that data products that I stress tested and we built at my project. So I'll give this mic to Xavier, and he will talk about it.
So thank you, Deepesh. So in the framework of our collaboration and evaluating, platform to do data science, we've been working with Deepesh on some simple data processing using Spark, the Spark notebook, and H2O, because one of the characteristics of data scientists is that they want access to different valuable libraries. They know a lot about different methodologies to get the best out of the data, and the best service that we can do as provider of technologies is give them access to really a wide range of libraries. So when you're choosing a platform that is a development platform, you want to have hands in many different technologies. And so this is just to illustrate the fact that it's quite easy actually to integrate into some platforms, and specifically the Spark notebook, something like H2O. So it's just a simple example. The Spark notebook is very similar in interface to IPython because it's the same basis. So you have cells, you type code, execute it. It's the same as the Databricks cloud-like interface. So what we did here is a simple process. The idea is that maybe I should make it larger. We take some data from Yahoo Finance, get it on our server from their public server. We will parse that data, put it somewhere in Parquet, then have another notebook that will read that data, clean it, make it in the right format, because we want to predict the value of one stock from the value of the others, so that we have a proxy, for example, for the American Express price taken from the others. That's a silly use case, but you have some use for it in real life setup if you want to find some arbitrage situation, or if you want to work with markets that are open at different times, you may need proxies like that. So it's just a simple example where we do machine learning. So this is the way the notebook works, and it's a Scala conference, and I like to say that, okay, you're in Scala, you're in a notebook, you want everything to be self-consistent in the notebook, so why not do from time to time, a system call to get data that is outside of the world, getting in local, and then saving it in your infrastructure, in your data lake. So that's the goal of this notebook. Very simple. So you see, you have these system calls, and directly the only thing we do here, we see that the data is consistent locally, but we want to get rid of that. That is not sustainable. So directly we read the data with Spark. There might be a lot of data. Here is just a little sample. And also the value of Scala, of course, is that you use, easily your case classes to be able to parse structures that may be a little tricky. We all like to play with dates, right? And when it comes to data, we often have them. So here I have my specific parser and my specific structure, because I want to be able to point to day, month, year maybe, and I have a timestamp. So this is my structure, the way I read my data, and I have the structure to build my price, which is, a stock name, a date, and simply a price. And parsing the data is just, for each line, you will parse the line, get a quote object. If it's well embedded with the options here, I can get a clean data set in some way. So no stray data should get in. I have no errors. And then it's pretty simple. I create a data frame out of it. So it's something that is having the structure of rows. So it's a set of rows, and each row has a schema. So I have, a string, the date structure that I just created. And when I save it on file as a Parquet file, if I read it again, I have for free the schema that was saved. So that's really an elegant way to do that. So that's the first notebook. Take data from the outside world, getting it into my storage infrastructure. Then, of course, I want to do something with this data. So I have a second notebook that aims to process with H2O this data set. So again, very simple operation. I read data in Parquet format, and when I do that, I get, as I said, the same schema for free. So that's the power, I would say, of these frameworks. But then I want to do something that is a bit out of the SQL space. So I have data that basically means one row is pointing to a single point, which is a stock symbol, a date, and a price. And because I want to compare the price for each date for different stocks, that means that what I want in a row actually is the price of each stock. So I need to gather together a number of rows and make them columns. And expressing that in SQL is pretty hard. That means that I want to get out of the SQL space. And that's the value, I would say, of the Spark interface. You work with data frames, with the SQL world. But if you're not comfortable with some transformation, you just go back to the RDD world. You get back into a very functional language space where you can do whatever you want with the structure you want. And that's exactly what this notebook is doing. So first I have a cleaning setup. I don't enter the details. It's not very important here. What's interesting mostly here is that in this filtering is that I use the leverage of SQL, because I do a join, an inner join, to remove wrong data. So that's something that I find really cool in those interfaces. And then I convert to RDD. Strongly typed with my strings long double, very easy to convert a row into a tuple of objects that I have here. And then, grouping things together by date and ordering in such a way that I have the right column that I wanted, and I set the right name on the right columns when I go back to a data frame, and I have exactly what I wanted at the start. That means each column represents the price of a given stock for different dates. I have removed the dates out of it. I just want to see correlations in the price. Okay, and it's not very long code, but conceptually it's quite tricky. You wouldn't do that in SQL only. And then we get into the interesting part. I could do that with MLlib, but I want more than that. I want to leverage the power of H2O. Who is familiar with H2O here? Very few. So H2O is really a great framework for distributed machine learning. The reason is that they have their own implementation of MapReduce in memory, so distributed. But the fact that they are working with linear algebra and machine learning makes that their structure is really optimized for working with floats, categories, and stuff. So it's really extremely performant. So it's really good to work with that. And the way it works, Spark, they have these workers, so distributed workers. And when I do this operation of creating an H2O context, what happens actually is that I will create an H2O worker living within each worker of Spark. So I have a cluster of H2O nodes living into my cluster of Spark. And when I have a data frame, I can actually ask for conversion of this Spark data frame into an H2O frame, and it's a memory-to-memory operation. So one partition translates into a partition from the other framework. It's just amazingly fast. And that's exactly what's happening here. You see, I have my data frame here, and I say, oh, convert it for me in an implicit way into an H2O frame, bam. And this data, actually, you can browse in the H2O interface here, because they have their own notebook. So now I have two notebooks living together, my master notebook, where I want all my code to be sustainable, I would say. That's the Spark notebook. But I can explore what's happening in memory on the H2O side here. So if I click on Get Frame, I see that I have here my main data set, this data frame here. And I have some statistics. So that's really pretty cool. And then I use the framework to make training and test set here, and I then call for the linear regression on this data set and get a model out of it. And then I don't want to work anymore into my H2O. I have my model. I have I want to make some prediction because it's living in there in H2O and see what's the result. And so I have operations to say that, okay, on the model you make a prediction here. I want it back as a data frame, a Spark data frame, and then I extract this data and just take the right column, which is the double with all the prediction, and I will zip it with the actual value and collect it in the form of an array. So I have an array of double, and if I ask for a display of this array, what I get is a table, so the prediction and the actual value, and I have several ways to plot it. So, oh, cool, there is a correlation between my prediction and the actual result. That makes a bit of sense. Then, of course, you can compute other stuff like mean square error, whatever. What I want to point here at this stage is the fact that we've been doing something very classical. You have a data set, you write code in a notebook, you process it, you get an output somewhere that is saved. And then when we take that output, we read it from a notebook, we process it, we generate a model, and how do we keep track of all this information? Actually, there's a way in the Spark notebook, in the Enterprise edition, that just allows to do that. So we generate from the work of the data scientist a view of what is happening here. That is, I have data in Parquet format. It has been read by code that is in a notebook. So if I take this part and this data in Parquet has been read by another notebook with code, generated a model, which is actually data saved somewhere. And it can go on and go on and go on. And so it's a platform that allows you to know that some data set has been used for some certain purpose, that from this data set you have clean version of it that is available. And so that's a very important feature, I think, of modern platform, is to get, an automated way to collect information about all that is being done by your data scientist. I will leave Deepesh make a conclusion.
So as you've seen, that there are many other different tutorials that I have uploaded on. So there are many other tutorials like this I have uploaded on my GitHub repo, and you can use them to go through them and learn more about it. Some tutorials were more than 40 minutes, so I just tried to squeeze as much as I can in 2 sessions. Thank you so much for your time.